Hi, my name is William Wilden, and my SPED talk today is on image hashing. So one of the things about my project is that you, I have to identify one image of something and compare it to another. For example, my project uses magic cards. So the left image is a picture that I took of a magic card with my camera, and the right image is a picture of the card uh, of, and that's the stock image of it. Now, the problem is how to get one to essentially see the other, or how to get them to see each other, how to compare them successfully with as few false positives as possible. So, what a lot of people might suggest is maybe, oh, they have the same name, so perhaps just some text recognition would be best. Oh well, I unfortunately am unable to do that as there are cards with the same name that have different art. For example, this one right here, which is very different from the one on the left. While functionally the same, I need to be able to tell between different editions of the same card. This also doesn't take into account very weird cards such as maybe one of these, which is very different. Um, Also, we have the problem that there's over 70,000 different unique magic cards, which makes things a little challenging. Makes it so that we can't just use machine learning just to learn all the cards for us and be able to identify it. So, uh, the, so the answer to the problem that we have is image hashing, and there's several different image hashes that we could use, but for my use case in particular, um, we're going to be using P hashes or um, perceptual hashes. Now, before we get into perceptual hashes, we have to understand something called the discrete cosine transform. Essentially, um, essentially hashing out data to and compressing data into a smaller form. The JPEG compression algorithm also uses discrete cosine transforms, which we'll see here in a bit. So the theory behind discrete cosine transforms goes something like this. If you have a cosine wave, okay, and you make the top of the wave completely white, and then you make the bottom of the wave completely black, what you get is an image that looks kind of like this. So of course, there's more than just one different type of cosine wave. You have cosine waves with varying frequencies. So the cosine wave on the left was the one that we saw earlier with a lower frequency, and the one on the right is a cosine wave with a higher frequency. And now if we take these two different cosine waves, add them together, and average them out, you get a wave that looks like this purple wave here. And then when we make that purple wave into an image, we get the image on the bottom, which is not something that you can make with just one cosine wave. So when you combine different cosine waves, uh, you get different potential images. So now that we know that, here's 60, and the JPEG compression. The JPEG compression uses 64 uh, cosine waves or an 8 by 8 DCT. If we start in the upper left, we get the low frequency waves, and as we move further down or further right, um, we get higher frequency waves. And as we take those frequency waves and add them together, we will get an image. So as an example, uh, let's imagine let's imagine we're doing the discrete cosine transform of this 8 by 8 pixel image of the letter A. By using all these cosine waves and then weighting them appropriately, some negative, some positive, we see that we see that adding them all these different cosine waves together will get you this 8 by 8 pixel image of the letter A. And so that's a little bit about how discrete cosine transforms work. You essentially take all these weighted cosines and then you get an image that's very close to the original image. So now that we know about discrete cosine transforms, we're going to use that in our p-hash algorithm. Uh, and so for our p-hash example, we're going to use this picture of the actress Allison Hannigan. And the reason why I'm using this picture is because the website that had the best explanation on p-hashes also used the same picture. So we're gonna go ahead and just use this. So uh, for the step, so to p-hash, the very first thing that we're going to do is reduce the size to 32 by 32. As you can see on the right, that's not just 32 pixels. I just took the 32 by 32 images and enlarged it so that you would be able to see a lot better. So now that and the reason why we reduced the size is to make it a lot smaller, to be able to run the DCT algorithm through it a lot cleaner. Same thing with this second step, which is grayscaling the image. You could run the DCT on images that still have color on them, and it would work just fine. Uh, but well, but we're not trying to just compress an image. We're trying to get it down to a hash so we can do comparison. So turning it into grayscale is pretty accurate to what we want to do. Um, Also, reducing it to grayscale also means there's significantly less comparisons that we have to do. So now that we turn into a grayscale image, we now run the DCT over it. Now the DCT that we saw earlier was an 8x8 DCT, and the DCT table that we're going to use for this one is a 32 by 32. And the reason why we do that is to make it a lot more accurate. We're using this to compare images, so we need to be as accurate as we possibly can, more accurate than the eye can see. Now, I know this is going to sound very weird after I just said that, but after we do that, we reduce the DCT to an 8 by 8, essentially throwing out a lot of the cosine waves. We throw out all the weights that we had in the lower right, and the reason why we throw out the ones in the lower right is because the the algorithm, the cosine waves in the lower right have a very tiny effect on the image. And so to get it down to its most base image, we just use the cosine waves in the upper left. So after we have that, we now have 8 by 8. We now have an 8 by 8. We have essentially 64 cosine waves that are all weighted differently. And now that we have that, we compute the average value of those weights of the DCT. And after we have the average value, we reduce those DCT weight values to 1 or to 0. And essentially, because there's 64 different cosine waves that we've reduced it to, this will give us a nice 64-bit number of those ones and zeros. And the hexadecimal number that you see on the bottom is the hexadecimal representation of that 64-bit number. Now, if we take that number and then run it back through the DCT, the 32 by 32 DCT, again to uncompress it, we get like a little fingerprint image that we see on the right. Now you might think, oh, that's just a bunch of white and black blobs. But what's fairly interesting about this, it's something that comes to light when we compare to the original. So when we compare it to the original, you might notice a few patterns here and there. For example, the head is pretty accurately still represented. The left, you can still kind of make out a head out of the fingerprint. Also, the fingerprint was also able to see this little this dark floor area that's a little bit darker than the rest of the walls. So now that we made that comparison, we now have a fingerprint. We have a 64-bit number, or 64 ones and zeros that represent the image. Now that we have that, we now need to compare it with other images. So we calculate that using what's called a Hamming distance. Essentially, what a Hamming distance is that if you take a binary representation of a number, like this one, and then you compare it to other binary numbers, whichever, um, however many bits that those binary numbers are different, that is the Hamming distance. So imagine we have an image that we're trying to compare, okay, and this is the binary number. So now what we do is that we get another binary number of a image in our library, okay? So so we have this binary number of another image, and I've highlighted here the bits that are different. So this has a Hamming distance of 4, which means it's probably pretty similar. And now let's compare with a different image. This different image has a Hamming distance of 12. There's 12 bits that are different, which means it's probably not very similar at all. So now that we have a Hamming distance, uh, the first image is probably going to be a lot closer to the original than the second image. And that's how we're able to compare two different images. So to recap the presentation, the steps to compare images with each other, you first get a library of source images. And then once you get the source images, you run the p-hash algorithm through all those images, and then you store the 64-bit number of those images. Now that we've done that, let's say we took a picture of a card, okay, and we run the p-hash algorithm through that picture of a card. And now that we have a p-hash algorithm of the card that I took a picture of with the camera, we now compare the hashes and we run the p-hash algorithm through it. We now compare the hashes of the card I took a picture of with the camera and the source images that uh, that I p-hashed, and then compare those hashes with the Hamming distance. And whichever source image has the least Hamming distance, that image is going to be the one that our our card is representing. So whichever has the lowest Hamming distance is probably similar to the image that I took a picture of. So I hope you learned a lot about how image comparisons work and how perceptual hashes work. Like I said, there are other different hashes that you can use that are faster and less computational intensive, but uh, I personally need a lot of accuracy in mine, and this is probably the most accurate way to do it. Thank you and have a good day.